I have a great question for you to test your abstract reasoning skills and your ability to use variables versus units. Here's the question. At this school, there are 20 students for every one teacher. I'd like you to turn that sentence into an equation where capital S is a variable for students and T is a variable for teachers. Go ahead and pause, think, and do some physics here. This is an important skill, and you'll get some immediate feedback to see where you're at in your ability to convert language into symbols correctly. So pause, think, and do some physics. All right, let's take a look. Don't worry if you got this wrong. It's actually often missed by even students who are enrolled in a physics class in college for the first time and taking calculus. This comes out of some great math research historically. So the answer is that students is, or the variable, capital S, that represents students is equal to 20 times t. And if you got that backwards, if you said t is equal to 20s, you might have been thinking of these letters S and T as units instead of what they really are in this question, which are variables. And with variables, we plug numbers into them and we can solve for quantities. So for example here, we could plug in for some random number of teachers. Maybe some school had 3 teachers, and obviously then we would get 60 students. Okay, so S would equal 60, which would represent the number of students. Okay, so a nice quick test of understanding to see if you can distinguish between variables and units in the context of turning this language into math. And that's very important in physics because we're often thinking about the world in our minds with language, and we're talking about physics in language. And we have to be able to convert that language into math and then back the other way again so we can make sense of it all. So this is kind of one of these first examples of testing your ability to do that correctly. Let's try another example. What if you had a job where you made $30 an hour? I'd like you to write a formula where we're going to invent these two variables here. One will be income, which will represent how much money that you make in dollars if you work a certain amount of hours. And then time worked will be represented by the variable capital T. And let's write a formula that would allow you to predict how much money you would make if you worked any number of hours. So pause the video and try it. All right, well, hopefully you got something, and I'll go ahead and write out a common response. So you might have done something like this. I'm going to leave a little space there. And if you did something like that, you almost got it right, but you've left off one important thing. You in this example, have correctly identified that these are variables, I for income, T for time worked. But if you were to plug in, for example, with this formula, the way it currently stands, say 3 hours, well, we would get 30 times 3 hours. And if we just follow the units here, this would give us 90 hours. And that would say that our income is equal to 90 hours. That doesn't make any physical sense. So in the real world of physics and science, we have to be very careful with our units because they have meaning about physical quantities. So you can see what the problem is here, I hope, and how to figure out the solution. If you did not get, or if you got this wrong, pause the video and see if you can get the solution. If not, and you got it right, well, then we'll see what it is right now. Okay, so the solution is to put in the correct units. And so this is $30 per hour. And now it should work out perfectly fine. We can come over here and we can find that our income is equal to $30 per hour. So that is a unit. Let me just be real explicit about that. Okay, this is a unit. And then multiplied by some random number of hours I'm making up right now on the spot. So there we go. And we can see that these hours cancel with those hours, and we're left with dollars, which makes perfect sense. So now we're getting a value of $90. And I'll just put the dollars there, even though we usually write it the other way when we're working with money. Cool, so it worked. Now it's also important to think about this relationship graphically as well. So we'll make a little plot, a little quick plot over here. And by convention, what's over on the left-hand side of an equation here, in this case, the variable income, that's going to be plotted on the vertical axis. So following our conventions, we would write out the name of the variable income here. And then we would, or typically what I like to do is also put in the variable, so income, comma, I, and then put in parentheses the unit, so that would be dollars. We would also have a title. I'm not going to bother doing that right now, but it would be descriptive title. And then we would have time worked. Here, capital T is our variable, and then our unit is hours. All right, so what would this look like graphically? Well, if you just look at the equation, hopefully you can see, and I'll put this in a different color. Maybe I'll just do green. This is good old y is equal to some slope m, some x, which is our horizontal variable here. So we've got x, but it's not x, it's capital T. That's the variable here in this particular instance. Well, it's not y, okay, y. It's income, capital I. And then, you would have a plus b in certain instances. But in this case, we don't have a plus b, so it's just y is equal to mx. And we would draw our line, and if this were an experiment, we'd have data points and we'd do a line of best fit, but in this case, we're just graphing kind of a straight up math equation. And our slope of this line would be what, right? Well, it would be, you should know this, $30 per hour. All right, great. So seeing this not only algebraically, but also graphically. And I've got one more question for you here in this video. This is a really great question. Actually, a couple more questions I forgot because we're going to be talking about subscripts as well in just a second. But before that, I want you to take this value, $30 per hour, and I want you to say that out loud or maybe write it down on a piece of paper without using the word per. Okay, so let me just write it out real quick. $30 per hour. Say that out loud or write it out loud, but you are not allowed to use the word per at all. Go for it. Okay, so hopefully you got it. And we would say that a person makes $30 for every, what comes next? Well, you might just say for every hour. Let's be more explicit than that. For every 1 hour. So we see that the word one shows up for the thing in the denominator, no matter what's in the denominator there. $30 for every 1 hour. What if we had something like this, $30, which would be pretty awesome. $30 for every 1 second. I would like that a lot. And so you could do this over and over again. Just to give you a little test of your ability to try this, let me make up some just total nonsense units to take the context out of everything. So for example, let's do something like 30, I'm just making this up, 30 Zambles over Quandles. I don't know, I'm just making up nonsense words. I have no idea if those words have any meaning in the real world. I hope they don't. But try this. Write it out as a sentence, just like we did above. Pause, think, and do some physics. All right, here it is. There are 30 Zambles for every 1 Quandle. There are 30 Zambles for every 1 Quandle. I have no idea what a Zamble is. I have no idea what a Quandle is. And interestingly, often when you're first learning something in physics, you also might have really no idea or having or an intuition really about what a quantity is. You might still be developing that knowledge. So it might seem like that these things almost sound just like Zambles and Quandles to you because you're just not there yet on your understanding. So it's important to know this kind of procedural method for understanding these values of kind of rise over run slope values and how to say and think about them explicitly. Okay, I'll give you one more thought here about that just to finally test your understanding. Now, something like this, you can say very clearly, 30 miles for every 1 hour. So that means if you're traveling at that speed forever and ever and ever, for every 1 hour, you're going to go forwards by 30 miles. So after 2 hours, 60 miles, 3 hours, 90 miles, etc., etc., etc. Okay, excellent. So we'll finish up here now thinking about subscripts. All right, subscripts are pretty easy, and the whole idea is just to be able to distinguish different objects. So for example, maybe you have car 1 and car 2, and you just want to make sure that you keep track of everything carefully. So the position of car 1 is equal to the velocity of car 1 multiplied by the amount of time car 1 travels for. This is just a simple formula here that you might have seen before in a previous kind of physical science course, and we're going to get a lot more specific in this in due time. But just to distinguish that from this other car, car 2, it would have a subscript x2, v2, and t2, and this would help you keep everything straight. Watch out when things get a little bit more complicated. We might see something kind of like this. I'm just going to make something up. So you might see this, and this is time for some object number 1. So that's the subscript that refers to object number 1. And then this 2, what do you think that is? Is that another object? No, that's a mathematical operation like squaring this time. So just watch out. Sometimes what people do is they'll, just to be real explicit, they'll do something like this, T1, and then they'll put in parentheses squared, just to make it real clear. I tend to not do that, but just some tips there. Okay, all right, so that wraps it up. A nice little video here on variables, units, and subscripts and how it kind of all ties together with this abstract reasoning. We'll see you in the next video.